Okay, I know one problem had a lot of writing where I asked you to solve by simplex method and carrying out and write everything, okay? So there'll be some good news today towards the end of the class. We'll have another way of writing it, which is more compact, okay? But that homework was important to just to get us really familiar with what to do. Okay, all right, so now last time we started this chapter that actually in the end the goal was to cover the whole algorithm for simplex method, but we had to cut it in half and we didn't finish, so we have to finish it today. Let's pick up the setting of the problem, all right? So from last time, and then we'll finish it, okay? So we have the problem in canonical form. We call it problem I. Minimize Z with the following. So we write it in canonical form. So I will write only the first equation and the last equation. Okay, so these are the basic variables, and here are the non-basic ones. Okay, so that's actually all the constraint up to here, and then we have the objective function. Is that right? So we assume that this is in canonical form, which means the basic solution has to be feasible. So all the right-hand side, all these BI's shall not be negative. Otherwise, we'll give a non-feasible basic solution. Is that right? Okay. So this is the starting point of a simplex method. And last time we had two theorems basically telling us in two situations we can terminate the algorithm, which the algorithm is still to be explained. So theorem O gives us the optimality. So in what situation would we know that we have reached the optimal value, the minimum value for Z? Anybody remembers? Where did we check? The coefficients in the objective function, right? If they are all non-negative, then you're done. That's what the theorem says. I'm not going to repeat the theorem. I'll just write it. If Cj's are bigger than equal to 0 for j from m plus 1 all the way to n, then we have reached the minimum. Is that right? So Z min, where do we find the minimum value? It's on the table. That guy, is that right? But not exactly that guy, but the negative of it. Is that right? That's where you find. And it's attained. Where is it attained? Because that's the step you have to write out your conclusion, right? You're finished. Attained at a basic solution. For if it's in this form, the basic solution will be B1, Bm for the basic variables, and 0 for all the non-basic ones. Okay? So that's a step where we would say, okay, that's done. And there's also another scenario where we call it theorem U. U for unbounded. That's the case where you actually have unbounded minimum. So let's see, did I try to use the same notation? Okay, so if now there is some index k where you find out one of the ck's are strictly less than 0. Okay, so let's say there is a ck, xk, and you find that this ck is strictly less than 0. And then you have to look at this column, all the coefficients in front of xk, right? And then you check and you find out there are less than equal to 0. So a, I, k's are less than equal to 0 for all I running from 1 to m, right? All of these here are 0. Then what do you conclude? Well, you know the minimum for this z will be unbounded below. Is that right? That's the second theorem, theorem U. And today we'll cover the case where these two, none of them would apply. Actually, in our discussion last time, this is called the case 3. Okay, so let's focus on that. So case 3 is the following case. So there is a k that ck is less than 0. So we're not in case theorem O. We are in the case of theorem U, but not that. So one of them is actually strictly positive. Okay, so and a, I, k strictly bigger than 0 for some I, at least one, and there might be more. It's okay? So we actually had all this in the discussion when we had the concrete example. I'm just writing down the same thing now in some general setting, kind of abstract. So instead of a 2, 3, I have a, I, k, and that's it. Is that okay? It's just the general writing. Okay. So, and if that is the case, and let's consider the ith equation. Okay. So let's say I have an ith equation. Here I have that's a, I, k, x, k, where this guy is strictly positive and this guy is negative. Okay, in that situation. So that means I would try to put xk as one of the basic variable, and I need to figure out which one of the old set should be replaced, right? That was the task. So I'll write out this equation, setting all the other non-basic one to be 0, and this equation will have only two terms. That is xi, that's the one xi there, plus a, I, k, x, k shall equal to b, I. Is that right? That will be that equation. It will be xi, that's non-zero, and this is non-zero. All the others are still 0 because they will be non-basic. Okay. Okay. And then what we did was we rewrite this as xi equals to bi minus aik xk. So we express xi in terms of our candidate for basic solution. I need to figure out what constraints I have to put on xk, right? So this is non-negative, and I have that constraint. Is that right? So you solve this inequality here, you get the following. Xk shall be less than equal to, you move this to the right-hand side, divide both sides by this a. So I have b I over a I. Okay. Is that right? So this is actually a real constraint. It gives me a condition for xk. Xk has to be bounded by that number. And this number right now is positive because bi is bigger than equal to 0, aik is bigger than 0. Right? A bounded finite non-negative number on the right-hand side, which bounds my xk. Is that right? So each of the aik that is strictly bigger than 0 will give me a constraint. So I'll have to go through all of these aiks where they are positive and check all the constraints. They must all be satisfied. Is that right? Basically, I need to nail down the one that is the strictest, which is the most strict one. you find the intersection of all these constraints. So what will be more strict, a constraint like this? Of course, it's bigger than 0. That's implied, and that's a positive number. What will be a more strict constraint will be when this number is as small as possible. Is that right? And this suggests the following algorithm. So this suggests the following. So I have a suggestion. So what do? Well, I need to find the minimum of that ratio. Is that right? So I need to first compute all the ratios. Okay, there might be multiple of them, but at least one. So bi over aik, where aik is strictly bigger than 0. You have to compute all of them. There might be multiple of them. And then find the smallest. And actually, what matters is the index of the smallest one. Okay, so let's say, give it an index. Let's say it's attained at index s for small. So bs over ask is the minimum of all these ratios, bi aik, where aik is strictly bigger than 0. The set of all these ratios. Okay, let's say the minimum is attained by where I equals to some s. Okay, I pick one. So you know s exists at least at one point, right? This is a set of just some numbers. There is a minimum. Okay. Okay, and then what will be your conclusion? Well, then the conclusion will be now replace. I will do the following. I will replace now this xs here by my xk as basic variable. Is that right? And that's basically what we did in that example. Is that right? So that the stricter one gives me which one I need to replace. Okay, and then I have the new basic variables. There will be the following. There will be the set of xi, I from 1 to m. That's the old set, except the s I take out. So this gives me m minus 1 of this, and then I add the xk into it. So I have m basic variables. Okay, and then here it is clear that this k is strictly bigger than m. Is that right? K is one of these. It starts from m plus 1, m plus 2, all the way to m. It's bigger than m. Is that clear? Right? Okay, and then a basic solution. Well, all the others I am not nailing down. I'm in particular interested in the basic solution for the new one, for this xk that I'm bringing in. So xk will be taking it will push the boundary, right? It will take as big as possible without violating the constraint. That will be the one you will be taking in the basic solution. Okay. Okay. And I also would like to know what will happen to the z value at this basic solution. Do I actually have a z value that's smaller by taking this step or not? All right? So look at the z value. So for this new basic solution, what will be the z? So the objective function is given here. If I rewrite it, I will have z equals to negative z0, if I move that to the left, and then plus all these x's, which are still non-basic variable except xk. Is that right? That one is bringing into the basic one. All the others are non-basic, meaning I'll still set them to be 0. Is that right? The only one that will be non-zero now is the one that I bring into the basic set. All right? Is it clear? That will be the new z value. So let's plug in. What do we have? So I have z0 plus, I have the expression for xk, this bs. So ck times this ratio, the minimum of this ratio. Okay. So do you think the z value is now decreasing? Sorry, lost the negative sign. Do you think the z value is decreasing? Before I do that, the z value is negative z0, right? Now, after making this switch of a basic variable, now I have negative z0 plus an additional term. So is this additional term negative that actually decreases my z or not? What will be the sign of this guy here? So let's talk. What do we have? I check the signs. CK, is it positive or negative? In this discussion, negative. Is that right? BS is some right-hand side, right? We know it's bigger than or equal to 0. And ASK, what would that be? Well, all of these A that we computed the ratio is strictly bigger than 0. Is that right? Strictly bigger than 0. So what can you conclude for this guy here? This guy here should be less than equal to 0. Right? And it equals to 0 only when BS is 0. Otherwise, it's strictly less than 0. Is that clear? Okay, so z will decrease, at least not increase, right? Okay, so let's put up this kind of a theorem. It's more like an algorithm, so we call it theorem M. That is actually the method, the simplex method, the key step, okay? The step that you keep iterating until you hit either theorem O or theorem U that you can terminate. Okay, so this is the one you have to perform many times. All right, okay, so let's summarize this in the theorem. It's basically what I wrote here, but we stated. Okay, so in this LP problem I, the canonical form, okay, so assume we have the following. We have some C, for some index CK is less than 0, and at least one AIK is strictly bigger than 0. For some I is from 1 to m. Okay? Then you know you have to compute this ratio here and find the minimum. And suppose I found it. Suppose I have this minimum. So let me copy again. BS ASK is the minimum of BI AIK. All right. 1 less than I m, and AIK strictly bigger than 0. Suppose that I found this minimum of this ratio for positive AIKs, and the ratio is attained at some index S. Okay? It could be attained at multiple places, but let's say we pick the S. Okay. And then what one should do, well, one should perform this iteration step. So what we need to do will be basically I need to replace x s by xk as basic variable. Okay? And you can perform pivoting. And you will have the new canonical form. Okay? And you can find the new basic solution, which will be feasible and at the basic solution, you will have the z value decreased. C will equal to negative z0 plus ckbs over as. Okay. Okay. And then you return your problem to a canonical form. So in principle, you could rearrange indices so that it will look like I again, and then you repeat. Is that clear? Mm-hmm. All right. So these three theorems, O, U, and M, are the ones that we would need to, in the end, just design this algorithm. This is the key step, and the other two will be conditions for you to terminate your iteration. All right? Let's say a few words about one situation here where kind of a trouble spot. Because, okay, so you have an algorithm here. You'll be interested in the following question. Okay, so this algorithm switch one basic variable with the other, and every step it does that. And how do I know that it will eventually lead to a minimal, to the solution? Will it just keep going on and on and on, getting stuck in a circle and never get out? Right? When you write a computer code with some algorithm, you have to always be careful it doesn't end up in a dead loop, right? Could that happen here? Okay. So that is an important thing to think about. So let's point out one thing that could cause trouble here. So make one little observation. From what we have discussed here, we see that we have two situations. If now at that minimum I have BS strictly bigger than 0, then Z will decrease. Is that right? Okay, let's put this up. Two cases. If BS is strictly bigger than 0, and then what we can conclude, and Z will, let me write down, decrease, actually strictly. Okay, it will be strictly smaller after you perform this step and after you're pivoting, after changing the basic variables. Okay? But on the other hand, if BS shall equal to 0, what happened to your objective function, the value for it, after you make this iteration? Well, what you have here will be just a big 0, and Z will not be changed. Is that right? So Z remains the same. It's unchanged. That is not very nice. I did all that work, and it does not even make the Z any smaller. Is that right? So this case has a name. Maybe we have mentioned it, but in a different setting. So this case is called degenerate. So if that happens and you say the linear programming problem is degenerate, okay, and it's a potential trouble, we'll argue a little bit, you see. Okay. So for now, I will have a discussion now to show that the theorem N here actually, as a iteration step, as a method, you only need to apply it finitely many times, and you will reach the optimal, the minimum for z, for this problem, if it is non-degenerate. Okay, so we have to assume that. For now, assume the LPI is non-degenerate. So what do we mean by that? That means the right-hand side, BI here, are strictly positive. There's no zero on the right-hand side. Okay, the zeros are the ones that give me degeneracy. Okay. And then for my problem, I'll have, in principle, I actually have two cases. Theoretically, the minimization problem. So first of all, I know it's in canonical form. It has a feasible solution. So there shall be a solution. It's always feasible here. It's not a non-feasible case. Then there are two cases. One is that the minimum is unbounded, right? And the second one is the minimum is bounded. Okay? So let's write this. So I have two possibilities that I need to figure out. The min is unbounded below. That means it goes to negative infinity. It can be as small as you want. And then the second case is the min is bounded. Okay, so I want to say we can handle all of these. So if you shall be in the first case that the minimum is unbounded, then theorem U will detect it. So one could use theorem U, the theorem for the unbounded minimum case, and then you will be able to detect it, and you can terminate your algorithm once you detect that. Okay, so that is the easy case. And then for the second case, where the minimum is bounded, actually, and then you know you'll be applying theorem M. So I will use theorem M, and then you can stop. So for the second case, I'll be using the theorem M. And you know theorem M is an iteration method, right? So you have to use it possibly many times until you reach the optimal, until you can apply theorem O. Is that right? But then the big question now is, how do I know after finite many steps I will be able to apply theorem O, that I will be at the minimum? Will it be possible that I get stuck by applying this step? Okay? So here I want to convince you that you don't need to go to infinitely many steps. There's a finite number of steps, guaranteed you will find the minimum in this case. Okay. So let's take a closer look at theorem M in the case where I am non-degenerate. Okay? So if it's non-degenerate in theorem M, after one iteration, what happened to the z-value? Z-value here equals to this after one iteration, and it's strictly decreasing. Is that right? This guy here will be strictly negative because B now is not 0. Is that clear? So in theorem, Z will strictly decrease. Okay, each step, let's call it a step. So you will get a smaller Z value. How does it help my argument? So you know that the Z value we're talking about are the Z values at the basic solution. Is that right? Feasible basic solution. So you find one feasible basic solution, and you look around and check all neighbor basic feasible solutions, and you find one that will make you strictly smaller, and then you move to that one. That's basically what that step M does, right? And then from that one on, you repeat and you look for one that is make you strictly decreasing, and you move to that one until you hit the minimal. So if every time the z-value is strictly decreasing, then you will never go back and revisit an old basic solution that you previously have visited. Do we see that? Because that one will have a certain z-value that will be strictly bigger than the one you have now. And you will never go back because each step you decrease. Do we see the argument? So every time you will go to a new basic solution. Okay, so it will so that conclude the following. So each time you will switch to a new, totally different, previously not visited basic solutions, feasible solutions. Okay? So now I only need to argue that the total number of feasible basic solutions are finite for this problem. So I just need to get an estimate on that. So let's see, what will be the total number of all basic solutions for this problem? What does that equal to? So you know, for each choice of a set of basic variable, you will have a basic solution, right? Some of them are feasible, some of them are not. If you're only talking about the feasible ones, then you know this should be actually bounded by the total number of choices of basic variables. Do we agree? If I have chosen, let's say, from x1 to xm, that's my basic variable, then I have a basic solution which is determined. Do we agree? And that is bigger than the total number of feasible basic solutions. Okay. So now here's the question now. So what will be the total possible combination of choosing m different variables from n variable? How many would that be? Are we familiar with this notation? I will be choosing m out of n. Is that right? So what does that equal to actually in the end? Anyone remembers? Yeah, exactly. Is that high school stuff, or did we learn that? I don't know where we learned it. Somewhere. Permutations, right? And you know, that is a finite number. Not too big, actually. It's okay, some number. So you know, at most, if you're so unfortunate, you actually visited all the basic solutions. At most, after this many steps, you would have found the minimum. And then your algorithm can stop. That's right? Provided that it's non-degenerate, of course. Do we agree? So this is, I will use this as a kind of a, so this is an algorithm. Of course, you worry about if it converges or not, and the term is called convergence. So we will use this as some kind of a, this, we say that is a proof of the convergence of this algorithm. Okay? Convergence of simplex. Okay, but here we assume the non-degeneracy. Okay, so only for that, for non-degenerate linear programming problems. Okay. Because the algorithm, this argument breaks down if it is degenerate. Do you see that? Let's take a look at what can go wrong if I am in a situation that is degenerate. Then it's not very nice if the LP is degenerate. Well, I can still perform the step in theorem M, but after performing the step M, the z value is unchanged. Is that right? So maybe I have a bunch of zeros on the right-hand side. In B, there are several equations, each one to give me the degeneracy. It could happen that I would just be circling around between them and keep going on forever without changing the z value, if the algorithm is not designed in a smart way. You could, in principle, follow in this. Is that right? Okay, so z remains unchanged after step. Okay, so if it's unchanged, then we cannot use this argument that z is strictly smaller, that each time you switch to a new basic solution. That argument cannot be applied anymore. You could be visiting an old basic solution that you visited maybe 2 steps before, and then you keep circling, okay? So what happens is this is called circling. This can happen. And then you're stuck. You're in a dead loop. Okay? So in your textbook, there is an example of circling in the appendix. If you're curious, you can go and take a look. Okay. But in practice, there are things that you can do to avoid circling. So it's not that all bad news. All right. Are we okay? Now, there's still a couple of things that is a little bit unclear, right? So we talked about a lot of things, okay? It's kind of a big and complicated algorithm. So this is, in the end, the key step that you have to do. And in this key step, there are a few things we have not actually nailed down. So first, you find a ck that is less than 0. What if there are several of them that's less than 0? Which one do you choose? It is not explained here. Is that right? If you want to tell the computer to do something, you have to tell him every step. He does not decide. You have to tell him. He's just following the orders. So that is not specified. And also, when you look for this ratio here, when you look for the minimum, if the minimum is attained at several indexes, let's say the first and the third, they both equal to 0.3, which is the minimum. Which one do you choose? You still have to make a decision. Is that right? So as an algorithm, there's still a few things we need to nail down. So what I will give you next is some kind of a big summary, and actually it's just writing out this simplex algorithm, one version of it. Okay? All right, so I'll leave that there. Let's okay, so I call this the big summary. Okay, and it's a kind of the algorithm also. So starting point, canonical form. Okay, so we always start from canonical form. And maybe next class we'll talk about how to put a LP into canonical form. There is a standard trick one can play. Okay, but let's don't get into that today. All right, so what will be my algorithm? So I'll be just using these 3 theorems, theorem U, theorem O, and theorem M, okay, referring to them as you need. So first, once I have that, first step, I want to check if optimality is achieved. If all Cj or Ci are bigger than equal to 0, then you conclude Z-min is achieved. What is the Z-min value? Is negative Z0, and then you stop your algorithm, right? That's 1. And then 2, if now I have the following, if there exists a ck that is actually less than 0. So one of them is less than 0. And I find out that the coefficient on that column here, all these AIKs, are less than equal to 0. And then I will quote theorem U. I will use that. I will say Z min is unbounded below. And then I stop also, right? So here I stop as well. So here I apply theorem O. Okay? And then third case is when the first two, they don't apply. So otherwise, what do? Well, I know I'll have to do a pivoting step following theorem M. So pivot by theorem M. Okay? And then let's nail down a few details, exactly what does the algorithm do. So basically, you have to choose first which one of these x will I pick to enter the basic one, and then second, which one will I replace. Is that right? So which one do I pick? So one of the c's are negative. There can be multiple of them. So which one do I pick? Well, I will pick the one that's most negative. So the column that I will choose with the, let's use this word, most negative CJ term. Is it clear what I mean? Most negative? That it's negative with a big absolute value. Is that okay? So I did not define. All right? Okay, let's say this is column given index K. So I picked K. And then I need to figure out which one I should replace by following the theorem, by doing this minimum, find the minimum. And if in that case, the minimum is attained at more than one index, okay? So the second is to find the row, right? Which row I will be pivoting. To find the row, okay. So you will be doing that, and then if the minimum is attained at multiple index, okay, let's say at I equals to 1 and I equals to 5. They both attain the minimum. Then you have to make a choice, right? So we will choose the smallest index. It's just a choice. You can choose otherwise. Also, you can come up with other criterions of choosing it. But that's a commonly used one. Okay? And then you perform one step of pivoting. You put it in canonical form again, and then you repeat the whole thing. So repeat from 1. Again, until it converges. Is that okay? Any questions? We okay? What we have to do? So that's basically the algorithm, okay? The step is in the theorem M. Okay, so what I plan to do now is actually we really need to solidify this knowledge, this algorithm here. What I will do will be we go through one concrete example. All right? So, and then you see this algorithm in action, and then you understand what to do at every step. Is that okay? I know we had a problem in homework with 2 constraints. but it doesn't hurt to see another example. Would that be okay? And I also want to make a point of leading this to the discussion of the next topic. All right? Okay. So let's take an example. So, okay. All right. So I want to minimize z always with the following. Let me write it. x1. I have 3 constraints. Okay. 2x4. And then, so these 3 are my actual constraint, and the objective function, I write it here. Okay, so I write it on purpose this way that everything is lined up, is clear, all right? And of course, all the x's are non-negative. That's understood, so I didn't write that down. Okay, so where do we start? I want to check if the optimal place is reached. So what do? I look at my objective function. I check the coefficients, right? Are they all positive? Nope. So I have not reached the optimal yet. I found that one of them is negative. Okay, so this is negative. Then what do I have to do next? So, okay, step 2, I check if all of these are less than or equal to 0. Is that the case? No, that's negative, but these other 2 are positive. So I am not at step 2. So I have to move to step 3. Is that clear? So I see that 2 of them are actually positive. Then I need to compute the ratio, right? So compute ratios. So 10 over 2 is 5. 18 over 6 is 3. So the ratio between this and that, and this and that, which one is smaller? That's smaller. Is that right? Which is this guy. So that means I am going to pivot x4 in equation 3. Okay, let's label the equations. 1, 2, 3, 4. Is that clear? So to my conclusion, pivot x4 in equation 3. Do we all know how to do that step? So making this decision is the important thing. You have to make the right decision, because you know after you made the decision, it's quite a bit of work to carry this out. Is that right? So you don't want to do that and find out, oops, I made a wrong decision. Okay, so how do we do this? So you know each equation will be replaced by a new one. And how do we replace them? So equation 3 is now being pivoted for x4. So I will take the old equation 3 and multiply by 1/6. I have to make it 1 in front. Is that right? And then what do I do with equation 1? I need to cancel that term. This and this and this, they all have to be 0. That's basically what I have to do. So I'll take equation 3, multiply it by the ratio of these coefficients, and take the negative. Is that right? Before I put it on top. So it will be negative 2 over 6, which is negative 1/3, and I add it on top of equation 1 to make that guy 0. Is that clear? Okay, so equation 2 will be the same. Equation 3 multiplied by 1/6, add it on top of 2, and then the last one will be equation 4. So I take equation 3, multiply by 1/3, add on top of equation 4. Is that right? So actually each step is all quite repetitive, and you just have to do it over and over without messing up. So let's write down the new one. So I have x1 negative 1/3, x3, 3, x5 equals to 4, x2, 1/6, 7. So you have some annoying numbers coming, actually fractions. Okay, so these are the constraints, and you did the same thing for the objective function. That's what you will get if you carry out this indicated operation. So 1 prime, 2 prime, 3 prime, 4 prime. Let's label these equations. So is it clear how this is being worked out? Okay, now repeat. Let's check again. Am I in the optimal situation? Does theorem O apply here? Are both of these positive? Nope. This is -1, so nope. Okay, now theorem U. Are all of these less than equal to 0? Nope. This one is positive, right? Okay, now we go to theorem M. Okay, I need to find the ratio of this over that for this is positive and find the minimum of it. And here I actually get only one ratio, is that right? 4/3, which will be the minimum among himself, just one person. So this one will be your choice. Is that clear? So what you will have to do now, your conclusion, I will pivot x5 in equation 1. So is it clear how to reach this conclusion? You should be able to do that. Okay, this is the basic algorithm. Later it gets more complicated with degeneracy and other troubles. Okay, this is the basic one. Okay. Okay, now how do we pivot this guy in equation 1? Let's see. We want to multiply. We want to modify all these equations. So I perform this pivot. So what do we do with equation 1? Well, I have to make this 1, right? So that shall be multiplied by 1/3. Is that right? What about equation 2? I need to cancel this guy here from here. So I'll take 1 prime, multiply it by 7/3, add on top of 2 to cancel that. Is that right? All right. So once you circle that, make the choice, that's where I pivot. The rest is the standard procedure that you have to carry out, right? That's that. So, and then I'll take equation 1, multiply. I want to cancel this one, so I will need to multiply by 2/3, add on top of 3. And then the last equation, I will take 1 and multiply by 1/3, add it on 4. Okay? Is it clear what you have to do? Okay, this is just write out. And you can do it whichever way you prefer. You have to make all these 0. That's your goal. Okay? So if I do that, I'll have the following. 1/3, x1, 1/9, x3, x5 equal to 4/3, 7/3, x1, x2, 11, so some annoying fractions, 2/3, x1, And then the last one. Okay, that's what I get. So, do you think I can stop now? Have I reached any where I can apply theorem O or theorem U? So now, looking at the objective function, what happens to these two coefficients? Is any of them less than 0? Nope, they're both positive. So then we can apply theorem O and we stop, right? So we do not need to iterate anymore. We have reached the minimum. So we finalize and write down the conclusion. So what is the minimum of Z here? Do we have that number on the board? Where do you find it? This number, is that right? But not exactly this number, the negative of it, right? So that equals to 202 over 3. So where is it attained? What is the associated basic solution? How do you find that out? So it's attained by the basic solution of this set of equations in canonical form, right? So where are the basic variables? Single them out. x2, x4, x5. These are the basic variables, right? And they would equal to whatever is on the right-hand side. And the non-basic one will be 0. Is that clear? So could you tell me what I should put down? What is for x1? 0. Where do I find the value for x2? That one. What about x3? It's non-basic. Is that right? Where do I find the value for x4? That one. And x5? That one. Then you finished it. Is that okay? All right. Now, quite some writing, and actually I cheated. I didn't write out the detailed computation here. I just say, you do this, and that's what you get. There will be quite some writing on the side to reach to this, right? Okay, even with all those skipped, I'm thinking I'm doing too much writing here. Do you agree? I'm putting up all these x3, 3, 3, 3, x5, 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 and I also put this in an organized way. If it is so organized, and I don't need to write this x3 because then I will know from the position of these coefficients which variable they stand in front of. Agree? So I could probably streamline the presentation of this calculation in a better organized way, probably less writing. Okay, so let me introduce that. Okay, so this is called, so I will put everything in a tableau, okay? That's the next chapter. The Simplex tableau. Okay, so I will only collect the coefficients. I will not write all these x everywhere. So we'll take the same example and we'll represent it in this new form. Okay, let's get very comfortable in this new form. Okay, so this is x1, column x2, x3, x4, x5, and then there is a column here where I store the right-hand side, and I've cut the line to mean there's an equal sign here. Okay, so it's different. And let's put the numbers in. 1, 0, 0, 2, -1, 10, 0, 1, 0, -1, -5, 20, 0, 0, 1, 6, -12, 18. There I put all the constraints, right? So let me draw a line to separate. I'm done with the constraints, and now I put the objective function 0, 0, 0, -2, and 3, and 60. I only put the numbers. I don't put the z's there, okay? So probably you will want to specify that these 3 are the basic variables, so I will identify them on the left. So you have always a clear view of what are the basic variables. Is that clear? x1 for that, x2 for that, x3 for that. They're in canonical form. All right? Okay. So that is the initial tableau. And then you start your computation. Okay. So I draw a line so to see that here is the objective function, here are the constraints. Okay. If it still bothers you, you could put a z here to indicate that it eventually is the z value you want to find. Is that okay? Okay, now let's look at these 2 coefficients. And we see that this guy is negative. So this column will be chosen to pivot, right? And which row do I pivot then? So what did we do in there? We computed the ratio, right? So let's do a kind of a side column for the ratio. So 10 over 2 is 5. This is negative. I don't compute. This is positive. 18 over 6 is 3. So which one has the smaller ratio? Is this one. Is that right? Which means this position will be chosen to pivot. Does that make sense? And then you put a circle on that 6. You know, that's where you pivot. And that's my choice here. And then I do this pivoting process. What you do is you take this column, think it's a vector, multiply by 1/6, and multiply this vector by 1/6 and add on top of that, make that 0, and just continue. Is that clear? Did we do similar thing in Math 220? When you solve linear equations writing in this detached coefficient form? So this is similar. It's a bit less writing. Okay, so if you do that, let me... okay, before we do that, we can also already know. So what do I mean after I circle this? I mean that x4 now will be a basic variable replacing x3. Is that clear? So I will have x1, x2, and now x4 as my basic. Okay, so after the pivoting, let me write out 1, 0. I'll be just copying those coefficients, actually. We have them. 4. So those are the constraints and the objective function. That's the end of the first step we took there. Okay, and now we check again the coefficient for the objective function. Now it's very clear, it's just down here, and then you see this is negative. So that column is now chosen to pivot. x5 will enter, and which one do I pick to replace? So which position will I pivot? So these are negative, I don't do it. This is positive. So 4 over 3 will be the ratio, and the smallest one between 1 is just that guy. That will be pivoted. So what does that mean is x5 enters and replaces x1. Is that clear? So I have x5 replaces x1, and then I have x2 and x4. Okay, and then you carry out this process, pivoting process. Pivot it right here, so I'll get the, let me copy the number, 1, 3, 1 over 3, 1 over 9, 1, 4 over 3, 7 over 3, 1, 0, 0, 2 over 3, 0, okay, and then the last one, the objective, I get 1/3, 1/9, 0, 0, 2, 0, 2, 3. Okay, and then you know these coefficients are the ones that you have to check, and then you see that they are both bigger than 0. So you're done, right? This is representing exactly the same thing as we did here, but I just write it in a more compact form. So from this table, how do you extract your final conclusion? What do you write? So the z value will be here. The negative of that will be the z. So you will write z min is equal to 202 over 3 and attained at, you need to find the basic solution. Now in this tabular form, it's very easy to find the basic solution. So x5 is right here, x2 is right here, x4 is right here, and all the other x's are 0. And that's it. Is that clear? Where to find everything? These numbers are important numbers in the end, right? So you can write x1 is not, so 0. x2 is here, 97 over 3. x3 is non-basic. x4 is here. And then x5 is there. So what do you think? Do you like this new way of writing? So we agreed on presenting the thing in this form. You have to remember, you have to know what this table means, all right? And it makes this writing more compact, okay? And then once we found an easier way of presenting all these things, and we will not go back to the more complicated one over here. Is it okay? Are we comfortable presenting everything just in this table? And you know, if you shall take one more step, the table will just get longer, right? No, not table, tableau, okay? We'll grow a bit longer until all the coefficients here, until you don't see any negative thing here, or you see one is negative and all these are negative, then it's unbounded, then you stop, right? Is that okay? All right. So in this table, actually the heavy computation is all hidden, the pivoting process. You choose this and you do the pivoting, and the details you have to do by side, okay? So I think I will have you practicing maybe doing one problem by hand in this tabular form, but then I think you are thinking in the back of your mind that this should probably be done by some computer algorithm. Do we agree? That will make life so much easier. All you need to do is decide, okay, computer, pivot right here, then he generates that for you, because that is done. Once you decide, it's done. And then you check, you say, okay, pivot here for me, and then he will do the computation for you. Okay, so next time I'll bring my computer. Okay, I could probably log on there, I don't know. And then we'll have a little software that we'll play with. All right? Thank you.